Okay, so I wrote the definition of functor on the board. Bartosz said it in words last time, but here it is. You have two categories. So a category is kind of a network of relationships. And here we have some objects, but they have almost no relationship except being different. Whereas in a category, you have all sorts of objects, but there's like notions of morphism between them, and you know how morphisms compose. And so a category is a network of relationships, and if I had two different categories, I could say, how are those networks of relationships related? And the idea is that to relate to the way that category theorists thought was the most appropriate way to relate to categories, there could be other notions of relationship, but this is the one that's most used and is called functor, is the relationship between two categories should say, for every object in C, give me an object in D. And for every morphism in C, no matter what two objects it's between, but C1 and C2, you give me a morphism in D from f of C1 to f of C2. So it takes objects in C to objects in D, morphisms in C to morphisms in D, and it's subject to two constraints. F of the identity should be the identity, and f of composition should be composition of f's. That's what it says to do. And so now we'll talk about, it may or may not have been a mistake to put this on the backboard. It was deliberate, but it may have been wrong. But basically, that means it's going to disappear. So if you ever want to see the definition again, just ask me to raise it up. So let me give some examples of functors, and then I'll let you work out some. So 2, if you remember, was the category sometimes called the walking arrow. It looks like that. It's got 2 objects and 3 morphisms. I never draw identity morphisms. They're always secretly there. And I never draw composites if I don't need to. So this thing has 3 morphisms, 1, 2, 3. Everyone see it? OK, good. And you could ask, well, that's a category, so what are the functors? How many functors are there from 2 to 2? How many functors, period? OK, how many functors from 2 to 2? Question mark. So if these are my 2 categories, what are the functors between them? Well, every object, say A and B, needs an object to go to over here. And every morphism needs a morphism to go to. And the identities need to go to identities. So once you've decided where the objects go, you don't need to worry about the identity morphisms anymore. So can anyone say how many functors there are?
4.
Someone says 4. OK, can you list where the objects went in each of your 4 cases? Where did A go?
A to A and B to B.
OK, A went to A and B went to B. In number 2?
B, A.
OK, next?
A,
A and BB?
yeah.
OK, so one of these is not like the others. Which one fails?
B to A?
Yeah, this one fails. And the reason, if you sent B to A and A to B, then I'm going to ask you where you send your morphism. It has to go from B to A.
If we had another arrow going from, yes.
Then we'd be fine, but we'd get even more functors. Would we? No, we would. That would be great. That would be the end.
Yeah.
Yep. Great. So there are 3 functors. And how many functors are there from 2 to 1? Let's say 1 is the category that looks like this. And say 3 is the category that looks like this. So if you want to start working ahead, how many functors are there from 2 to 1? From 2 to 1. For the people who want to work ahead, they can ask that question, or they can ask this question. OK, so how many functors are there from 2 to 1?
So A is 1 and 2.
Sorry?
2.
2.
A is 1.
A is 1.
So
A maps to 1. And
I'm asking.
I didn't catch it. Yeah, I'll try to get it, but yeah. Somehow I must have caused confusion because I'm getting questions that are confusing me.
You numbered the dot with a 1.
I did, didn't I? A. A, B, C. OK. How many functors are there from this category to this category? 1. You say where the objects go. Where do you send this arrow? You need to send it somewhere. You send it to the identity. OK, so there's one of these. How many of these are there? How many functors from 2 to 3? Yeah. You can send everyone to A. You could do A, B, A, B, B. Am I doing a weird order? Why did I do it that way? Anyway, B, 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 C, 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 B, C, C. What did I do?
2 columns. 2 columns. Can you explain what this notation is?
Oh! OK. So I'm going to send everything in each one of these things to either A, B, or C, and then check whether that was actually a functor or not. And basically, you could send them both to A. You could send both A and B. You could send one to A, one to B. You could send one to A and one to C. So let's ask about this one in a second. You could send both to B. You could send both to C, and, or you could do that. OK. So this one is an interesting one. What does it do on the morphism, the unique morphism here? It maps to the composition, which is not drawn. So I don't draw compositions unless I have to, and I don't draw. There's secretly drawn here. There's secretly a morphism, and this diagram secretly commutes. I just want to ask, is this confusing? Are you with me or confusing? Good. I'm getting only yeses so far, so people need to tell me if it's not.
Can you say what commutes mean?
Commutes? Yeah. In a category, if you've got some objects and you've got some morphisms, then someone can ask whether that diagram commutes or not. And what they're asking is, I see 2 paths in the diagram. Do you want them, when I compose them, do you get the same answer in your category? A category knows not only objects and morphisms, but how to compose. So it can ask whether F composed G is equal to H composed I composed J. And saying something commutes means that this is true. They're asking, does this commute? They're saying, is this true? And you're saying, it commutes. And I draw a little check mark there, and that means it commutes.
So meaning it commutes is that both these...
that all the paths in the diagram...
They start and end the same.
No, these obviously start and end in the same place, yes, if you look. But it could be that they do not commute, in the sense that, like, you could have this set 1, 2 here, and all sorts of different weird maps. Maybe both things go here, and then this guy goes there. But in this one, something else happens. Like that. And if you follow something around, you'll see it ends up there versus there. And you get a different answer. And so the composite of this is different than that one, so it does not commute. And one person draws it like this, like there's a hole. Someone punctured this thing, and it's not really. It's like flying apart right now. OK, questions about any of this? Yeah?
Does the functor need to be invertible?
Are functors always invertible? No. So almost none of the functors we wrote down were invertible. Invertible means there's a functor going the other way, such that if I go round trip, whichever way place I start at and go round trip, I get back to the identity functor. I know if I compose functors, oh, that's something I should say. So if you compose functors, if you have a functor from C to D and a functor from D to E, then this one takes objects in C to objects in D. This one takes objects in D to objects in E. So together we get objects in D to objects in E. And same with morphisms. And if this one preserves identities and this one preserved identities, then so will the composite. So we can compose functors. And there's also an identity functor that says every object in C goes to itself and every morphism goes to itself. And 2 morphisms are inverse if when you compose them, you get back to the identity. And it is not the case that all functors are invertible. OK. Other questions? Yeah.
Is there a name for invertible functor?
An isomorphism. An isomorphism of categories.
Okay.
There's actually a better notion, better in some sense, called equivalence of categories. It's like less stringent, but still says that for all intents and purposes, they're the same. For many intents and purposes, they're the same. Just like isomorphism, for really almost every possible intent and purpose, they're the same. But maybe foo and bar is not for you the same as true and false, because this is easier to think about or whatever. So it depends on what you mean by all intents and purposes. But just there's a notion, there's isomorphism of categories. Other questions? OK. Let's see, 218. Great. Here's a question for people who already know lots of stuff, or for everyone. I guess I'll ask everyone. How many functors are there from set to 2? So turn to a neighbor and ask yourself, ask each other, 2 is this category that looks like that. And maybe it's fun to think about how many functors there are from set, the category of all sets and functions, to 2. Just as a weird exercise. So turn to a neighbor and talk for a minute or two. How many? You have any idea?
Is it just as many?
OK. Any ideas or questions? Yeah. Any ideas? Someone says 3. Other people? OK. So one person said it's 3. 2 people said it's 3. One person back there said it's 3. One person said it's 3 because there are 3 total morphisms in here. And by coincidence, everything I've talked about so far unfortunately had it the case that the number of functors from 2 to that category was exactly the number of morphisms. And that is not a coincidence. 2 happens to be the shape of the general morphism. And so the functors from 2 into anything are exactly the morphisms in that category, whether it's these or any other category you draw. Functors from 2 into C kind of like equal morphisms in C. And I'll put that in quotes because what does equal mean? But so there was a confusing thing, which is that all the examples I've given so far just counted the number of morphisms. And so you might say, oh, it's 3. So is that why you thought it was 3? So why did you say it was 3? 2 non-empty sets can't be on different sides of this, because for any 2 non-empty sets, there's a morphism going one way and going the other way. And they'd both need a place to live if set A was sent to this dot and set B was set to that dot, then the morphism going that way would not know where to land here. So if there's a morphism from B to A, it can't be that B's over here and A's over here. So basically, you can either put, and this is a stupid exercise that's never going to help you again, but you could either put the 3 functors are like all sets go to A, all sets go to B, or all empty set goes to A, all non-empty sets go to B. And the reason that one works is because there's no function from any set to the empty set. If you have a set with some dots in it, they all need a place to go, and so they can't go to the empty set. So anyway, weird example. Any other questions that come up? Yeah?
Is there a special name for the category where the objects are sets and morphisms are inclusions?
Yes. Is there a special name for the category where the objects are sets and the morphisms are inclusions? It's called the category of sets and inclusions. And every category theorist would know what you meant if you said that. So it is like, you could say sets and injections actually would be a better word. Other questions? OK. So now I want to talk about functors from set to set. And the reason to talk about these is that they're more like the ones you'll encounter in Haskell. So let me give some examples. One, like the identity. The identity is always a functor from any category to itself. It sends the set ABC to the set ABC and sends every function to itself. But maybe here's a better one. So like maybe the functor from set to set that sends A maps to. In LaTeX, this is written maps to. It means that this thing is being sent to, and it's a distinguished arrow from that kind. But whatever, OK. A is mapped to A times naturals. So this sends like ABC to the set ABC times the naturals. And what this means is the set like consisting of things like A comma 5 and B comma 12 and B comma 13 and C comma whatever. OK, so that's the set of pairs. And that's a functor. So if I have a function from ABC to 1, 2, 3, maybe I send A to 1, B to 1, and C to 2. Then what would I do to these three elements? Then what I'm supposed to get is a map from A times n to B times n. Because every object here is sent to an object, every set is sent to a set, and every morphism is sent to a morphism or function. So the function sending ABC to 1, 2, 3 like that needs to send every element of this A times n to an element of B times n. Where does it send A comma 5? 1 comma 5, yep. And then 1 comma 5, 1 comma, 1 comma 12, 2 comma 14. And then you should just check for yourself or check later that this is going to send identities to identities. And it's going to send composition to composition, and so it's a functor. If I did this twice, and I did it twice over here, it would match up correctly. Just think about it if it's not parsing. Yeah?
I'm confused. Isn't A cross n is all pairs?
All pairs, and I wrote 3 of them.
OK. It's not the subset of that. It's just all pairs.
It's all pairs. And when I say just think about it, if I ever say that, I mean think about it. If you don't get it, feel free to come up afterwards and ask, or even ask in class. Other questions? OK, so that is a functor. Another functor from set to set takes any A, any set A, and returns the set foo, comma, baz. This throws away A entirely, throws away A, and just returns this function, this set, sorry. So what does it do to a function from A to B? It's supposed to return a function. What function should it return? Let's just have it return the identity. OK, that is going to be a functor. It's called a constant functor because it sends everything constantly to foo, comma, baz again and again. This is constant. OK. Another functor sends, it goes from set to set because all the ones in this thing I'm talking about right now do. It sends A to list A. And if A is ABC, then list A contains things like the list bracket empty list. It contains A, B, B, C. It contains all lists where the entries in that list are taken from this set. Yeah.
So, like, it doesn't just go up to the length, to like the number of elements. Like, are they
all lists? Yep. Arbitrarily long lists. So you could call them words, like ABBC is a word. It can have repeated elements like ABBC. Yep. And it can be empty.
But there are finite. Right?
But there are finitely many elements in the list. The list stops at some point. And that's a functor. It sends every object in set to an object in set, namely A to the set of all lists in A. And if I had a function from ABC to 1, 2, 3, like the one before, then it sends a list of A's, like list A, B, B, C, to a list of 1, 2, 3s. And that list will be the same length, and it'll be 1, 2, 1, 1, 1, 2. And when I say it does that, that's not like automatic, that you should have just guessed what it did. It's that I'm defining a functor right now, and that's what my functor does. You could give another functor from set to set that sent A to list A, and maybe did a different thing, if you could think of what to do. Like maybe it doubles every list. Like it takes, maybe it does something fancy, who knows. But this one works, yeah.
So I know you're not supposed to like be able to look inside what an object is and see the elements of the set. So like, how do I think about this functor? How is the functor able to know what all the elements are? And
Right.
is able to get the set
So the question was, in category theory, we often say you're not allowed to look inside the elements, inside the objects, and say what their form is. So how come this functor is allowed to look inside the objects somehow? And the answer is that when someone gives you a category, they have to tell you what the objects are and what the morphisms are. And when I tell you the category of sets, I say that the objects are these things you can look inside of. Then, when I'm defining a functor, I'm allowed to use the data you told me about C and D to make that functor. So if I just said I have a functor from C to D, arbitrary C and D, I can't look inside because I don't know what's in there. Like the objects just are objects. But functors from set to set, the person constructing the functor is doing the work of looking inside and making things work. Person using the category doesn't ever have to know it. I think that's the distinction that we should be more saying, is that not that you can't look inside the objects or morphisms, but that you don't have to, and like, yeah. And you shouldn't ever do it as a user. Like it's a private method or something. Like you're not supposed to do that or you'll be kind of, yeah, it's a little subtle, but say again?
Violating the abstraction.
You're violating the abstraction. But when you're constructing the functor yourself, as the functor constructor person, you do get to use that information, and you'll have to use that information. Yeah.
But if let's say that someone gave us a functor, then if we don't look into the things, then we will not have this kind of meta-semantic understanding of that functor, what it is. Like if I could look into it, I can see that this functor is a map. But if I don't, it will be just a functor. So I can use it, but I will not understand what it is.
Yeah.
So in a sense, to be able to do like work with them meaningfully on a meta level, I have to look into it.
That's right. That's a really good point. If you didn't know what functor you were using, I just give you a functor from one category to another and say like, here's a great functor, like happy birthday, and you like you could just try it out lots and lots of times, like plugging in things into it and like pressing the button and seeing what it does. But it won't be as efficient as if you somehow understood like what it's doing. So yeah.
So just to clarify, you said that list A is finite, but also it includes lists that have repeated elements. How do you have a finite set of lists when you could just have repeat A infinitely?
Right. So the question was, I somehow said that list A had some finiteness to it, and but list A seems infinite because I could just write B, 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 B infinitely, like 43 billion times or 43 billion and one. What happened? What I meant to say, whether I said it or not, is that every element of list A is a list with finitely many elements in that list.
Okay. So
Not that this thing will always be infinite unless A is the empty set.
Okay, so it's the infinite, the list A is infinite because it's the set of all finite.
That's right. So list of what's called unit type, or list of the category of the set with one element in it, is isomorphic to the set of natural numbers, because like 1, 1, 1, 1 is sent to its length 4. So even when you have just one element, list of it is infinite already. But all of the lists have finitely many entries. Other questions? Yeah.
Is there a functor from A to stream A?
Is stream a functor from set to set? Yes. Stream is a functor from set to set that takes every set A to the set of functions from, I want to write this in so many different ways. I want to say that functions from n to a. And this is a that's a functor. Yeah. Okay. No, sorry. So there is a functor that takes a to stream a. And what I would do in my functor is, if you give me I would give this on objects. For every object, I'll give you for every set, I'll give you the set of streams. And for every morphism from A to B, I'll map that morphism over the stream, meaning I'll take my stream of A's and apply my function one at a time to get a stream of B's. That does not mean there's only one functor, but it's the only one I can think of right now. OK. So what we've seen is that categories, well, one thing we've seen, OK, that's the end of the set example part of the talk or class. And so categories themselves form a category. The collection of categories. There's a network of categories. Each category is like a network of relationships, right? A relationship network. But you can, there's a category where the objects are like C and D, and the morphisms are functors. So objects, so there's this category cat is a category. Just like set is a category, cat is a category. Its objects are all categories. If you're worried about size issues, the category of categories is bigger than each category in the category of categories. So, and cat CD is the category, is the set of all functors. OK. So the object, an object is a whole category, like to or set. And a morphism from to set is a functor from to to set. And you can compose functors, which I said over there, and you can have an identity functor for every object. And so it forms a category called cat. Any questions about that? Yeah.
Given two non-empty categories, is there always a functor between them?
Yes, between any two non-empty categories, there's a functor.
So there is actually a functor from cat to set, for example?
Yes, there are many functors from cat to set. So one functor from cat to set sends every category to the set foo, comma, baz. Another one, maybe the one you're thinking of, is it sends every category to its set of objects. And given any functor, I get a function from the set of objects of one to the set of objects of another. But maybe there's lots and lots of other ones also, similarly.
You mentioned about size issues. What about the categories of different sizes? Are there still functors?
Yes. There are still functors between categories of different sizes. Yeah. And by sizes, he means the notion of size that set theorists care about, which is like cardinalities, or maybe even what Grothendieck universe you're in. Care is needed in that area. Like if you want to have a category of all functors between two categories of different sizes, then come ask an expert or read about Grothendieck universes. But yes. OK, other questions? OK. Yeah.
When you said that, when you mentioned the size issue, like this category is bigger than the one that said, does that mean that you just define it to not include
yeah.
categories? Okay.
That's right. Yeah. Basically, yes. If you want more than basically, he said, how do you deal with size issues and stuff like that? And basically, you just don't let this category of all categories be inside of itself or anything of that size. But you don't let anything of that size be inside of this thing. But if you are worried about it, come talk to me. It's not the kind of thing that's going to help you work with categories. on the level of this class or think about them on the level of this class. So it's just like this weird thing that you have to deal with sometimes, and pretty rarely. OK, so in Haskell, to declare a functor, like you want to say, I have a functor thing from Hask to Hask. There is no category Hask, but there's almost like one of Haskell data types and functions. So sometimes I'll pretend that there is, in the sense that I'll use words from category theory to talk about things in Haskell, and it's as though I'm talking about this category Hask that doesn't technically exist. So when the first day I said, does category theory actually apply to anything? Does math actually apply to anything? Is it really just like 5 of anything in the real world? No. In some sense, it's all like an abstraction we're doing or a metaphor that like 5 glasses is the same as 5 cups is the same as 5 goats or whatever. But it can work pretty well. And so can this notion of functor work pretty well. So what do you do to declare a functor? You do 2 things. You declare a type constructor with 1 variable, and I'll say what that means. 1 type variable. And 2, you declare, let's call it f, that f is an instance of functor, the functor class. And what that part means is say what f map should mean. So that's what you have to do. What this corresponds to in category theory is that you have a function from obc or obhask to obhask, and you have a function from each hom set to hom set. That's what these 2 things are doing, and I'll say more in a second how it looks in Haskell. So let's say we wanted to do the one. What have we done so far? So one thing we did is times naturals. So like you write data. This is going to be our type constructor. Data with string A. And you don't need these parentheses, but we're declaring that with string is a type constructor with 1 free variable A, and that's the capital A from over there. And what it is with stir, it says like to invoke this functor, please write with stir, and then write something. So we're going to write with stir A comma string. And this is Haskell notation for A times string. So you say with string is a new type. And what type is it? It's the type A times string for any A. So object A, any Haskell data type A, which are the objects of Hask, is sent to object A comma string, which is how they write A times string. So that's the type constructor. And I'm allowed to use the same word here. Like I could write with string here, but maybe it's confusing to see it on both sides. Later, you'll see if you actually program in Haskell, or I think, it's more confusing to use a different name because you're always remembering 2 things. So it's actually less confusing eventually from my point of view and from most Haskell programmers' point of view to use the same data constructor as the name of your type constructor. But anyway, so this is us declaring what this functor does on objects. It takes A to A times string. And then we say, oh, and I'll tell you what to do on morphisms. In other words, I'll tell you that this is I'll tell you what f map should mean. So you'd write this, and then you'd say, oh, with string is a functor whereby f map. OK, so what is that f map f equals? This is how you'd write stuff. And what that's talking about is that f, it's inferring that f is a morphism from A to B, from type variable A to type variable B, from strings to integers or booleans to floats or whatever. And that's what it knows this f has to be. It infers that. And our job is to say what f of f from f of a to f of b is supposed to be. So we're supposed to write, so this thing is waiting here for a with string a, and this is waiting for a with string b. F map a, okay, F map a of with string this thing equals that. Okay, so this is asking, if someone gives me f from a to b, what am I supposed to do on my with string thing? And so what we answer is F map of, if someone invokes some x comma s, so if someone, this x is of type a, which is confusing again. Like, how am I supposed to remember that x is of type A? So Haskell people will write an A again. That's confusing to you because this is of type this. This is an element of that set. That's confusing. Which one's actually more confusing? In math class, this is confusing, and this makes sense. And we say x is in A. But in programming, it's easier if you just write A here. It just turns out, from my point of view and from Haskell that I've read. OK, so here comes, someone gives us an x comma string. S is of type string. And our job is to return something of type b comma string. And so what we use is with str f of x comma s. Someone told us how to map A's to B's already, so we just do that on our A part and return a b comma s. B comma string. If this is confusing, it's code for this, and you can ask afterwards. But as a functor, it shouldn't be confusing, because it wasn't confusing back then. As Haskell, it can be confusing because it's notation. OK, questions about that? Yeah.
Is there a close parentheses after the lowercase x?
Oh, yeah. So really, they would probably, they all just do that.
So that's 2 there, right?
Yeah, yeah. Sorry. I'm getting, OK. OK, other questions? Yes. This is probably not the only functor you can define, but it's the only one that I'm thinking of right now. Yeah, if you want, think about other functors you could define of that sort. OK, so after class, I'm happy to talk more about other functors. I was going to say more about them, but I'm going to go on to talk about natural transformations. OK. So basically, what is a natural transformation? Is a map between functors. And functors are already maps between categories. So it's kind of like a lot of layers here. And categories are already like lots and lots of maps between things. Just like maps and maps and maps everywhere. But basically, you have C and you have D. And you have these two functors, f and g. And the way people will draw this is like that. It goes from this one to this one. And the natural transformation is named alpha. And really what's going on is that this is like, well, the way Bartosz explained it was that C is kind of this network of relationships. So here's C, right? Sorry, this is the way he explained how his intuition for natural transformations to me. And D is this category. And if I have a functor between them, then it's like I have like C living in here in some shape. Some stuff, maybe two objects have been collapsed in here. And two morphisms go to the same place in here. But we know that, like, in general, things kind of look the same. Like they still have objects and morphisms are being sent over here, and composition still lines up and stuff like that. But it's like slightly warped a little bit, like slightly collapsed. Some information has been lost. But you know, like, yeah. And that's F. And G might send this same category to like some other shape. Maybe I'll try to draw it in the same way. So here's like F's version of C, and here's G's version of C. And they're kind of like related. Sorry, they look kind of similar because they're both indexed by C. Objects went to objects in both cases. Morphisms went to morphisms. And a natural transformation says for every object in this one, you both have an idea where it's supposed to go. Both F and G say it's supposed to go somewhere. And I'm going to draw an arrow between them in D. And I'm going to do that for each object in C. So it's like C, it's like maps, the maps occur in D. And at the behest of C, if that makes sense to you. In other words, C is like commandeering or like taking hold. C, there's two versions of C and D inside of D. And for each object, we get this morphism in D. All the actions happening in D, and it's all happening because of stuff in C. So I'll give the definition in a second. Yeah?
Does this always exist?
Do natural transformations exist between every two functors? No. I have to assume. I mean, I shouldn't have answered so quickly.
No.
I doubt it. I severely doubt it. Yeah, that's right. Great. So, so the first definition, and I'll answer your question with this first example, why it's no. Let's take C to be this category and D to be any category. Then a functor from C to D is the same thing as an object in D. The object went to an object, and the identity morphism went to the identity morphism. And so choosing a functor is the same as choosing an object. So suppose I have two different functors from C to D. Then I have two different objects in D. That's exactly what those two functors are. So what is a natural transformation between them? Oh, I didn't define natural transformation yet. But maybe it's still in. OK. So that's a teaser for you. And maybe you can use that to say why there's not always a natural transformation between every two functors. But let's give the definition. Let this be happening. So suppose you have two categories and two functors. I'm not going to write it out because of time. A natural transformation C to D, F to G, consists of like just one thing for each, well, for each C and C, a function, what we'll call it alpha C, from F of C to G of C. And satisfying one constraint, and this is the most important part, and this is like a check. The constraint is for each F colon C1 to C2, that's something in C, the diagram commutes. The following diagram commutes. Which diagram commutes? Well, I can do F of C1, I can do F of C2, and I can do F of F. FC1, C2 of F. Do you remember that from what a functor is? If I have a morphism in C, I get a morphism between F of C1 and F of C2. F sub C1, C2 of F. But I could also do that with G. I have this G sub C1, C2 of F. But I also have alpha C1, and I also have alpha C2. So I have a whole square for every morphism. For every object, I get a morphism. For every morphism, I get a square. And I want all those squares to commute. And then I have a natural transformation. So what is a natural transformation from F to G in this case? Any ideas? It's just a morphism, because for this object, I need a morphism. That's what this says. There's only one object to use. And for every morphism, I need to check this thing. But the only morphism in one is the identity. So it's saying, suppose I have like identity on top and identity on bottom, and I just have alpha C and alpha C in both places. Then does that commute? And it just says, is alpha composed with identity the same thing as identity composed alpha? And it just works. So that's another thing we can talk about after class, that you don't really need to worry about identities for this definition. Like they just automatically hold for part B. So the point is that the natural transformations from F to G are the morphisms. Brendan, did you have a question?
It's a very leading question, really. I personally would prefer that you don't use the word function in...
Did I say function?
If you agree with me, could you please explain why?
A morphism. Yep. A morphism in D. D is not the category of sets unless it is. And it's usually not, and therefore we don't call arbitrary morphisms functions. Thanks. Okay, so why don't you see, so why are there sometimes no natural transformations between functors? Well, because D could be the category that looks like this, and F could send, and G could send like that. And then there's no morphism like this. There's no morphism that way. There's no natural transformation this way. Yep.
Is the name natural? It doesn't refer to something in particular, natural transformation?
No, it doesn't refer to anything. It just means the people who invented it found that the way people talked in math when they said that something was a natural thing to do turned out to line up very well with this. Questions from people? Okay, so I'll let you go and come up afterwards if you have questions or comments.